Now let us understand the factors which affect the state of equilibrium. See, if we know, like suppose this example in which A moles of A combines with B moles of B changes to C moles of C and D moles of D is at the state of equilibrium, we know that the system will remain in the state of equilibrium. Now if suppose the factors which determines the state of the equilibrium like temperature, pressure, concentration, etc. are changed, definitely the state of the equilibrium gets disturbed. Now once the state of the equilibrium gets disturbed, it will try to move to the direction so that whatever the change which has been brought are neutralized. This was very well explained by a scientist called Le Chatelier, and that is how this is called the Le Chatelier's principle, which explains that whenever for a reaction which is at present at a state of the equilibrium, the factors that determines the equilibrium are disturbed, the equilibrium shifts in the direction so that the changes brought are neutralized. A very simple thing. Now let me make it write down so that you can understand what exactly this Le Chatelier's principle is. That whenever a change is brought by changing the factors that determines the state of equilibrium, the system moves and adjusts itself in such a way that the changes brought are neutralized. Now for this is what this Le Chatelier's principle is. But now first let us understand what all are the factors which helps us to determine the state of the equilibrium, and then whenever a change is brought into those factors, how the system readjusts itself so that the changes brought are neutralized. But the foremost important thing is to understand this Le Chatelier's principle. It is very similar to your normal physical balance whose pointer is exactly towards the middle. If anything is disturbed for that physical equilibrium or physical balance, we know that both of its left hand side and right hand side will start moving up and down. So the pointer also starts moving and down. Ultimately, it will move towards the side which is more dominating. The same thing is applied here. Whatever the change is brought, the system will readjust itself so that it attains again the state of the equilibrium. Now first let us understand the factors on which the equilibrium depends. Equilibrium I am talking about. Remember, we are not discussing the factors which affect equilibrium constant. We are only discussing the factors affecting the state of equilibrium. The first factor and the most important is the concentration. We will be taking them separately one by one. The second is the temperature. The third is the pressure. The fourth is the catalyst. And the fifth is the addition of the inert gas. So these are the major 5 factors which usually we study, which actually when changed, will readjust the state of the equilibrium for a reaction. Now let us understand the first factor, concentration, and how it affects the state of equilibrium. See, the concentration for any reaction which is at the state of equilibrium can be changed in two ways. Either addition of reactant or product is done, or removal of a reactant or product is done. Now we have to see these two one by one, how they affect the state of the equilibrium. Let us understand by taking an example of a reaction in which A moles of A changes to the B moles of B. We also know from the number line system, here on the left hand side we have the reactant A, and here on the product we have B. The system is exactly at equilibrium. It will be having a certain value which is equilibrium constant, K equilibrium, and this is exactly at the middle. Now suppose, and we know that this K equilibrium will be having the value B to the power B and A to the power A. Suppose addition of reactant is done. At the state of equilibrium, we have added the reactant to the reaction mixture. What will happen? The moment you add the reactant A to this reaction mixture, this denominator will become a larger value, because that you can predict only through your Q, because K equilibrium is only at the state of equilibrium. The moment you put A, the state of the equilibrium gets disturbed. Now how to find out what exactly where the reaction is? You know that you have done, it is a reaction quotient. So now this value of this Q, what you will find, will have a larger denominator. Now this bigger or larger denominator will make the value of this Q lesser than K equilibrium. And you know that when this Q is lesser than K equilibrium, it means what? The system is not towards the reactant side. What will happen? How it will readjust? It will move toward the forward side. So when the addition of reactant is done, the reaction, or you can write the equilibrium gets disturbed. It is more towards reactants side, and what will happen is, since it is towards reactant side, it will start moving towards the forward side, towards the product side. Therefore, rate of forward reaction gets increased, and so that whatever the amount of A you have added, immediately it starts getting consumed, gets converted into product, so that the more of the B is formed, the lesser the A becomes. The ratio of this two, which is your reaction quotient, again becomes equal to your K equilibrium. So if for any reaction at the state of equilibrium, if the reactant is added, the rate of the forward reaction gets increased. Remember, if the reactant is added, rate of forward reaction gets increased. Now let us see what happens when a product is added to a reaction mixture which is already at a state of equilibrium. We have an example in which A moles of A changes to B moles of B. We know the equilibrium expression, equilibrium constant, that it is B to the power B and it is A to the power A. And we know that this will be also equal to your Q, which is your reaction quotient is. Now, and we know from the number line that this is your reactant A and this is your product B. Now, if suppose for this reaction, which is already at a state of equilibrium, if B is added, definitely what is happening is, now the system will not be at equilibrium. We cannot express the concentration in terms of the K, it is Q, which is going to decide what exactly this value will be. Now, since now the B is more in the reaction mixture because we have added B product, B is added, the numerator value is much bigger, which will make this Q value much larger than, and it will become higher than this K equilibrium. And we know that when the value of the Q is much larger or greater than this value of K equilibrium, it is more towards the product side. So, when this Q is added, when product is added, the Q is greater than your K equilibrium constant, due to which, since this value of your numerator is larger, Q is bigger than K equilibrium, the reaction system will move towards the backward side. Rate of backward reaction will become higher, so that whatever the amount of the product which you have added gets consumed more in a faster way, so that more of the A is formed. The ratio of these two become again what? Equal to K equilibrium. So when the product is added, remember, rate of backward reaction gets increased. Of course, the system shifts towards the product side, but which rate gets increased? Backward rate gets increased, because the product has been added to it. So by this we have seen, if a reactant is added, rate of forward reaction gets increased. If a product is added, backward reaction gets increased. Now let us understand, if something is removed from the reaction mixture. Again, it will depend whatever we are removing. If it is reactant, how it gets changed. If a product is removed, how it will get changed. Let us see, in a similar situation, if suppose we have removal of reactant. If suppose A is removed by putting up something in the reaction mixture, suppose A has been absorbed back or it gets consumed. So the concentration of A is decreased. So the moment the concentration of A is decreased, we can make out from here this denominator value is smaller, this numerator value is larger. The Q will become what? More than this K equilibrium. So the removal of reactant will make this Q again larger than your K equilibrium. So what will happen? Since now you have more amount of the products, they will start reacting in a much faster way, so that more of the A is formed. So what will happen is, the rate of the backward reaction gets increased, so that more of the A is formed. The ratio of these two again becomes, this Q becomes equal to your K equilibrium. So what we find is, the removal of product always increases the rate of backward reaction. Rate of backward reaction gets increased. And that is why it is always advised, or in whatever the reactions which we do in the industries which involves equilibrium, we always keep on supplying the reactants so that it can move always in the forward direction. It can form more and more of the product. And we know that from the moment we withdraw the reactants, the rate of the backward reaction gets increased. The system moves towards the backward side. Now let us see what happens when the removal of the product is done. If removal of product is done, if in this system, suppose the B is removed. So when B is removed, the product is removed. Now I think you all can easily make out, this is lesser, numerator is lesser, denominator is a bigger value. This value of this Q will become lesser than your K equilibrium. So your Q is less than your K equilibrium. So what will happen is more of the reactants will react in a much faster way so that more of the B is formed. The reaction moves towards much faster in the forward direction. The ratios of these two becomes what? Similar to a K equilibrium constant. So what we find is removal of product always increases the rate of forward reaction. So this is how we have understood that how the concentration, its addition and removal of the reactants in the products makes difference to your equilibrium and to which direction it proceeds whenever any one of these is done.